Hello friends, welcome to my channel. In this video, I will cover GATE solution 2016 thermodynamics power plant heat transfer and refrigeration part I will cover. This is set 1 part 2. Question is a fluid Prandtl number given 1 at 500 Kelvin flows over a flat plate 1.5 meter length maintained at 300 Kelvin. The velocity of fluid is 10 meter per second assuming kinematic viscosity 30 into 10 to the power minus 6 meter square per second. The thermal boundary layer thickness in mm at 0.5 meter from the leading edge. How much we have to calculate? Thermal boundary layer means delta T we have to calculate at x equal to 0.5 meter. So Prandtl number, we know Prandtl number, our formula is boundary layer thickness divided by thermal boundary layer thickness to the power 1 by 3. Sorry, here it's Q PR to the power 1 by 3. Then fluid temperature given means T infinity 500 Kelvin. Flat plate total length is 1.5 meter maintained at surface temperature. Plate surface temperature is 300 Kelvin and velocity of fluid V infinity 10 meter per second. Kinematic viscosity 30 divided by 10 to the power 6 meter square per second. X value given 0.5 meter. So first we will calculate Prandtl number. Prandtl number already given, so first we will check flow whether it's laminar or turbulent. Reynolds number we will check. RE equal to rho VD by rho VL is characteristic length divided by coefficient of viscosity. Then VL dynamic viscosity. V is your 10 meter per second into length is 1.5 divided by kinematic viscosity is 30 divided by 10 to the power 6. 1 minute here. X is given 0.5. So length is 0.5. REX we have to calculate. So we will get 5 by 10, 10 cancel, here you will get 6. So 10 by 6, it's 5 by 3 into 10 to the power 5. So it's laminar. Up to 5 into 10 to the power 5, this is laminar. So this is less than this quantity, 5 into 10 to the power 5. So this is laminar flow. For laminar flow, our boundary layer is delta is 5 into x REX root over 5 into x is 0.5. Reynolds number we got 5 by 3 into 10 to the power 5 root over. If you solve this one, you will get 0.00612. This is in meter. So convert 6.12 mm. Prandtl number given PR to the power 1 by 3 is delta by thermal boundary layer thickness. So Prandtl number is 1. Delta T equal to delta 6.12 mm. This is your answer. This is fill in the blanks type question. So 6.12 mm. This is your answer. So here first we have to calculate Reynolds number, then types of flow, then boundary layer you will calculate, and from there you will calculate thermal boundary layer. Question is for water at 25 degrees Celsius dPS by dTs equal to 0.189 kilopascal per Kelvin. PS is the saturation pressure in kPa kilopascal and Ts is the saturation temperature in Kelvin, and the specific volume of dry saturated vapor is 43.38 meter cube per kg. Assume that the specific volume of liquid is negligible in comparison with that of vapor. Using the Clausius-Capron equation, an estimate of enthalpy of evaporation of water at 25 degrees Celsius in kilojoule per kg we have to calculate. So Clausius-Capron equation we will write first. P by dt at constant enthalpy HFG divided by T saturation into VFG. We have to calculate enthalpy of evaporation of water. So HFG we have to calculate. HFG equal to T saturation into VFG into dP by dt. So already given dP by dt 0.189 kilopascal per Kelvin. So put the value. Saturation temperature is 25 degrees Celsius. So Kelvin you write. VFG is 43.38 into your dP by dt is 0.189. Finally, if you solve this one, you will get 2443.24 kilojoule per kg. This is your answer. Only this formula you have to remember. Question is, an ideal gas undergoes a reversible process in which the pressure varies linearly with volume. The conditions at the start, subscript 1, and the end, subscript 2 of the process, with usual notation at P1 equal to 100 kilopascal, V1 equal to 0.2 meter cube, and P2 equal to 200 kilopascal, V2 equal to 0.1 meter cube, and the gas constant R equal to 0.275 kilojoule per kg Kelvin. The magnitude of the work required for the process in kilojoule is how much? So data given: P1 equal to 100 kilopascal, V1 equal to 0.2 meter cube, P2 200 kilopascal, V2 0.1 meter cube, R value 0.275 kilojoule per kg Kelvin. Linear relation. So PV diagram we will draw. We have to calculate work done, work required. This is from 1 to 2. V1, V2 given, P1, P2 also given. P2 is 200 kilopascal, P1 is 100 kilopascal, V2 is 0.1 meter cube, V1 0.2 meter cube. So area we have to calculate. Area is your area of this trapezium. Entire area we have to calculate. So this is work done or work required. Half into 200 minus 100 is 100. Then 100 plus 200 into height is 0.1, 0.2 minus 0.1, you will get half into 300 into 0.1. 0.1 you can write 1 by 10. So 15 kilojoule. This is your answer. Question is, in a steam power plant operating on an ideal Rankine cycle, superheated steam enters the turbine at 3 megapascal and 350 degrees centigrade. The condenser pressure is 75 kilopascal. The thermal efficiency of the cycle is how much? So data also given. So first we will start. Saturated liquid at 75. This is condenser pressure. Then one more pressure is given. This one for superheated. So Rankine cycle, we will draw the TS diagram. This is TS diagram. One to two, then 2 to 3. 3 is superheated. Then 3 to 4. 4 point we don't know. So 1 to pump work, 1 to 2 pump work, then 2 to 3 boiler, 3 to 4 turbine, 4 to 1 condenser. So here at saturated 4 dash. So data we will write first. Our P is this one, 75 kilopascal, constant pressure line. Here 3 megapascal or 3 megapascal. In kilopascal 3000 kilopascal. Then this temperature T3 given 350 degrees Celsius. Enthalpy also given H3. H3 is 3115.3 kilojoule per kg. 3 to 4 is isentropic process. So S3 equal to 7428 kilojoule per kg Kelvin. Same. S4 also same. Here HFG given. HFG means H4 dash minus H1, 2278.6 kilojoule per kg. S1 also given 1.213 kilojoule per kg Kelvin. Then S4 dash minus S1 or SF, it's 6.2434 kilojoule per kg Kelvin. First we have to calculate X value. Then we will calculate enthalpy at 4 point. Then here in this question they asked thermal efficiency. So thermal efficiency means work done divided by heat supplied. So at exist of turbine we will calculate dryness fraction. This point we will calculate dryness fraction. We know 3 to 4 is isentropic process. So S3 already we got. S3 equal to S4. It's equal to S4 equal to S1 plus X into SFG. So SFG is S1 plus X into S4 dash minus S1. We will calculate. So S3 is 6.7428. It's equal to S1 is here 1.213 plus dryness fraction into SFG. This is SFG at the rate 75 kilopascal. So we'll put that value directly, 6.2434. If you solve this one, X value you will get 0.885. Then we will calculate enthalpy at 4 point. H4 is H1 plus X into HFG at 75 kilopascal. So put the value. H1 is HF at 75 kilopascal. Its value given 384.39 plus dryness fraction we already got 0.885 into HFG at the rate 75 kilopascal, it's 2278.6. So finally you will get H4 equal to 2402.55 kilojoule per kg. Then we can calculate from here turbine work. Turbine work is H3 minus H4. We got already in question H3 value given, H4 value we got, H1 also given. Then this point H2 we have to calculate. Or for pump work, without H2 also we can calculate pump work. But for heat supplied, H2 is required. Pump work is, it's in liquid region. If you follow this curve, this side is liquid region. So it's more depend on pressure than the temperature. So pump work WP is VF1 into VF1 is at 75 kilopascal into P2 minus P1. P2 is 3 megapascal minus 75 kilopascal. Put the value 0.001037 into P2 is 3000 minus 75. You will get 3.033322 kilojoule per kg. This is pump work. So H2 value we have to calculate, because you have to calculate heat supplied in boiler. From 2 to 3 it's boiler. So H2 is H1 plus work done VF into P2 minus P1. H1 is HF1 at 75 kilopascal, it's 384.39 plus this value we already got, it's 3.033 22. So finally you will get 384 plus 387 something, you will get 387.42 kilojoule per kg you will get. So net work done is W net turbine work done minus pump work. So if you solve this one, turbine work is H3 minus H4. H4 we already got, minus pump work is H2 minus H1 divided by, okay, first so we will solve this one, then we will calculate efficiency, or directly also from here you can calculate. Efficiency is W net divided by heat supplied. W net is H3 minus H4 minus H2 minus H1 divided by heat supplied is boiler heat supplied H3 minus H2. Just put the data as 3115.3 already given in this question. H4 we already calculated. T402.55 minus H2 we calculated. Not required also. Directly you can write the pump work. 3 point something we got. 3.03322. 3.03322. Then H3 is 3115.3. H2 is H2 value 387 something. 387.42. 387.42. If you solve this one, finally you will get thermal efficiency equal to 0.2601 and percentage term 26.01%. This is your answer. So this is fill in the blanks type question. So you can write here 26.01%. This is your answer. This is the end of this video. Set 1 thermodynamics, heat transfer, power plant and refrigeration. Thank you friends. Thank you for watching my video. Thank you.